Imagine a particle hitting two slits. What does it do? You might think, yeah, I've seen that before, it goes through both slits. That's what quantum physics seems to imply, except it's not really true. Or, to be more precise, that's not the only option, because quantum physics isn't just a single theory. There is about a dozen of them, and they don't really agree on whether the particle goes through both slits, or just one. But the problem goes even deeper, because to agree where the particle goes, we first have to agree on what the particle actually is, and we absolutely don't. Just open a few videos on this topic and read the comments. When there are observers, they are particles. If not, they are waves. There are no particles and no waves, just quantum field decomposition. Cool, thanks. That clears up absolutely nothing. I find it amazing how we have built entire theory around particles, and somehow we still don't know what a particle is. So what do we really know about the quantum world? Let's break it down, one questionable idea at a time. Since like forever, everything in the universe used to obey this guy's laws. Yep, that's Newton. His equations worked flawlessly, right up until they didn't. Because once we started zooming in, and then kept zooming in, down to atoms, the entire idea of a particle being in just one place fell apart. As it turns out, a particle doesn't really have a single position, 3 numbers to tell us where it is. The universe says nope. So, to describe a particle, we now need a number at every single point in space. The particle now becomes basically a 3-dimensional Excel sheet. And that Excel sheet is what we call the wavefunction. And to make things even more confusing, now we also don't know how the particle moves. Quantum physics just says, this is how the Excel sheet shall change over time. And that, my friend, is the Schrodinger equation. Okay, so what the heck does this all even mean? Let's make our lives a little bit easier. We will look from one side, so that we only see 2 dimensions, and we will swap numbers for colors. Yep, that's what a wave function can look like. Now, let's add the 2 slits again. Wanna know what's going to happen? Well, just pull out the Schrodinger equation, crunch the numbers, and this pops out. Now, you might think, look, the particle just went through both slits, so it's in 2 places at once. Or, even worse, the particle moves like a wave, and even interferes with itself. So particles are actually waves. That's all very tempting, but not really correct. And the problem with all that is that nobody actually knows what the heck a wave function is. Is it something real? Or just abstract math with no physical meaning? Physicists don't really agree on this. There are many different theories. We call them interpretations. Terrible name, by the way, because these are not just different ways of explaining the same thing. They are completely different theories. And yes, it's exactly as weird as it sounds. In quantum physics, you can choose from many theories, and they all give the exact same predictions. But the problem is, they don't agree on what's actually going on behind the scenes. Each one would tell you a completely different story. Yet everybody usually talks about just one, the Copenhagen Interpretation. It's the most used one, but not because it makes the most sense, just because it came first and never left. And what does it actually say about what's going on behind the scenes? Well, not that much. It basically says the wave function isn't real. It's just a mathematical tool. Think of it like a black box. The theory makes correct predictions, so feel free to use it. But don't ask what's actually going on inside, because you're not getting any answers. For example, in the double slit experiment, we can predict where a particle will land, but we don't get any answer as to what the particle was doing along the way. How did it travel exactly? Which slit did it go through? The Copenhagen Interpretation says, I have no goddamn clue. The problem starts when we forget this, and we try to explain what's happening usually by identifying electron with the wave function. The wave function goes through both slits, so that means the electron goes through both slits as well, right? But that's not correct, because whatever bizarre stuff the wave function is doing, it doesn't mean at all that the electron is actually doing that. You might ask, why? Let's say we have 2 particles. Cool, just give each particle its own wave function, right? Nope, you don't get 2 wave functions, you only get one, and it describes both of the particles. And if you had million particles, still just one wave function. But now It's not a nice 3D thing we could visualize. It's a monster living in 3 million dimensions. So particle isn't its own wave function, but rather wave function is the description of the entire quantum system. Now, that's not the only issue with the wave function. There is another one. You might think that the wave function is like electric field, something invisible but measurable. But it's not. You can measure the electric field, just stick a detector next to some power lines and you get a number. But you cannot measure the wave function. There is no wave function detector. So as far as we can tell, it's not something that exists in nature. Or if it does, then for some reason it's completely hidden from us. Now obviously this begs a question. Why the hell did we came up with wave function if it doesn't tell us anything useful? Well, the wave function and even the Schrodinger equation are useless on their own. That's why 2 extra rules have been added to quantum physics. They are called the measurement rules. And that's where things get truly bizarre. In pretty much every theory ever, once you have your equations written down, they tell you how something evolves. And that's it. End of story. But in quantum physics, nothing is that simple, right? Sadly, yeah. And so, quantum physics operates in 2 stages. First stage is when you leave the system alone and let the Schrodinger equation do its thing. And the second stage is the moment you measure something, like a particle's position. That's when the wave function finally becomes useful. The bigger the number, the more likely is for the particle to show up there. That's the Born's rule. And this entire measurement thing is the weird part. Even Einstein hated it. You might think that he didn't like the randomness. The God does not play dice with universe. But his full sentence was: God plays dice and uses telepathic methods. I cannot believe that for a moment. And here is what he meant. Imagine you've got something unstable, like uranium atom. Or, let's be honest, probably your mental health. Anyway, the atom eventually spits out a particle. Where does it go? In the Copenhagen story, we don't know. The wave function spreads kind of everywhere, but the particle doesn't have a position. And it's not that it's hiding, its location is simply just not defined. Right until suddenly it subscribed to this channel. Maybe you should do that too. Right until suddenly a detector goes off. The particle shows up right here. In that instant, the wave function collapses. It snaps to a single point. And here is the wild part. That collapse doesn't just choose one location. It instantly erases every other possibility. Everywhere. Across the room, across the galaxy, doesn't matter. The chance of the particle showing up anywhere else drops to 0 instantly. It's like the universe decided, oh, it's there. In that case, kill every other possibility. And that's what Einstein called telepathy. Now, some scientists don't like this theory so much. They go as far as to say this isn't even real theory. Like this guy, Tim Maudlin. He put it like this. A proper theory should tell you 2 things. What exists and how it behaves. Copenhagen Interpretation, the mainstream quantum physics, does neither. It just hands you a recipe. Take the Schrodinger equation, plug in some numbers, and it will tell you how likely each outcome is. That's cool, but we have no clue what's actually going on underneath. And on top of all this, Copenhagen Interpretation comes with another catch. It never tells you what actually counts as a measurement. If a particle interacts with other particles, that's probably not a measurement. But what if it interacts with something bigger? A molecule? A virus? A cat? Does that count as a measurement? Or where the heck do we draw the line? Copenhagen's story has no answer, but it ends up implying something strange. The laws of nature somehow change, somewhere between an electron and a cat, but it never tells you where or why. Now obviously this theory isn't very convincing, and so other scientists started cooking up their own versions. 25 years after mainstream quantum physics was built, here comes Bohm with his pilot wave theory and says, the wave function is real, you just can't see it, brother. Okay, maybe that's not exactly what he said. Anyway, in his version, the particle is like a tiny boat, and the wave function is like the invisible current steering it. The current goes through both slits, but the boat, the particle, only goes through one. But Bohm's idea isn't the only alternative. One of the more bizarre ones is the many worlds interpretation. Here is how that one goes. The wave function is real, and actually it never collapses. Instead, when a measurement happens, every possible outcome becomes real, just in a different branch of reality. So here we end up with endlessly branching multiverse, which sounds cool, but please don't ask me what that means. But hey, at least there might be a version of you that actually understands quantum physics. And there is more, at least 10 other interpretations. But the issue is, there is no way to prove which one, if any, is actually right. They all make the same predictions when you measure something, but what is happening before you measure? Or if you are not measuring at all? We have no idea. There is just no way to check. So now we are left with two options. Either there is a single truth, one story and one theory, and it's just hidden from us. Or there simply isn't a single truth at all. Of these two options, the second one is more likely. And that's because there is something called contextuality. It's a feature of quantum physics that has been proven by experiments. Here is what it is. First, imagine a classical world, where objects have fixed properties. Let's say something is round, red and striped. You can measure the shape, the color and the pattern all at once, no problem. But in quantum physics, that's not how it works. Imagine a particle also has a shape, a pattern and a color. The first problem is you cannot measure all of them at once. That's the Heisenberg uncertainty principle. If you choose to measure shape and color, there is nothing you will know about the pattern. But it gets stranger. Even if you pick two properties that can be measured together, the result depends on which pair you choose. Measure shape and color, you might get round and red. Now, measure shape and pattern, suddenly it's squared and striped. The value you get for shape literally depends on what other property you measured alongside it. So it really seems that there isn't a single global truth. There isn't a hidden list of properties that is just waiting to be revealed. What you learn about the quantum system depends entirely on how you look at it. If you enjoyed this video, I also recommend this one. Don't forget to subscribe if you want more quantum madness, and see you next time.